and I'm going to try to maximize this function L by choosing x1, x2, and mu is going to show up as well. Okay, so this is, it's a different kind of maximization problem than the one you've been solving, but mechanically you can solve it in a very similar way. You just compute first order conditions. The first order conditions here are not difficult to come up with. In the general case, the partial derivative of L with respect to xi is just the price of that good. We get that from here. And then there's a term here involving minus mu times the partial derivative of u with respect to the ith good. And at the optimum, that has to be equal to 0. So we get one of these conditions for each good. And then finally, we get back the requirement that the utility that we get from consuming x1 and x2 has to actually achieve u star. Is that clear? Okay, let's try an example. So this is in the lecture notes, and I'm going to talk my way through it a little bit quickly because I don't want to get too bogged down in algebra. I don't want you to spend too much time writing algebra either. These notes will be online. Okay, so let's assume that we have the same kind of utility function we've been working with, and to generalize just a little bit by assuming that there's a subsistence level phi1 and phi2 for each of the two goods. So this is a quasi-homothetic utility function. Okay, so if we have this form of utility function, I'm going to go ahead and simplify things by figuring out what these marginal utilities are. So the marginal utility of good xi for this utility function is just alpha I divided by xi minus phi I. So this is a marginal utility of good I. Now, so I've got this thing. I want to remind you that this is the first order condition I care about. So, and what I just did was computed this piece, this du dxi. I just figured out what that was for the ith good. So I substitute that in. I use the fact that it's equal to 0 at the optimum, and I get the requirement that the price is going to be equal to this Lagrange multiplier mu times alpha I divided by xi minus mu I. So this piece is just the marginal utility. Okay, now here comes a trick, and maybe I should do it on the board. Let me try to talk my way through it though. No, I'll do it on the board. This is 2. So think about the first two goods. My conditions here are that p1 is equal to mu times alpha 1 divided by x1 minus phi1. That's the condition for the first order condition that's associated with x1. And then I got p2 equal to mu alpha 2 divided by x2 minus phi2. Those are the two conditions. Now I'm going to do a trick you've seen before, which I'm going to just divide. This mu actually does have a nice interpretation, but I don't want to deal with it right now. So I'm going to get rid of it by dividing one of these equations by the other. So I do that pretty simply by doing this basically. And that gives me p1 divided by p2 is going to be equal to alpha 1 divided by x1 minus phi1, all divided by alpha 2 divided by x2 minus phi2. This stuff over here simplifies a little bit and gives me the expression I have here on the bottom, namely the ratio of prices is equal to this ratio of expenditure shares, or these alphas, reference parameters, alpha 1 over alpha 2, times x2 divided by x1 minus the subsistence parameters phi1 and phi2. Okay. All right, now I want you to look at this equation, and I want to come back to the graph for a moment and just think about interpreting that thing. The thing on the left-hand side is the ratio of prices, which remember is just the slope of these budget lines. And the thing on the right-hand side, so what's this expression on the right-hand side? Oh, very good. So was that actually? Yeah, so the marginal rate of substitution. Yeah, that's exactly what this thing on the right-hand side is. So this is the same condition we had for the primal problem. Ratio of prices equal to the marginal rate of substitution. So that tells us that we're looking for a tangency between one of these indifference curves and this line having this slope. That's exactly right. Okay, so that's a familiar kind of condition. That doesn't quite solve the demands yet because we haven't yet made use of the constraint that we have to achieve this level of utility u star. Right? This price ratio equal to marginal rate of substitution is satisfied for a whole bunch of points that might go up here or something like that. So we have to figure out which one. We're going to do that by finding where this Isaac line intersects the indifference curve. Okay, so in particular, the other equation we need is this one, ux1, x2 equal to u star. Okay, so I've got this equation here. I've got this equation here. There are two unknowns, x1 and x2. I can solve that thing, and when I solve that thing, I'm going to get a new kind of demand out of it. What I'll get are called Hicksian demands. So we've been working with the Marshallian demands. These are Hicksian demands. Now, how are they different? They're different because the Hicksian demands, let me just write this up here because I'm not sure I have it on the slide. The Hicksian demands are going to depend not on prices income, but instead on prices and on u star, or the desired level of utility. Okay, now the Hicksian demands for this particular utility function actually have quite a nice form, but it takes a little bit of screwing around to get there. Here are the steps, I'm not going to drag you through them. You can verify them on your own. If I take the restriction here that I just got, and then work with this expression for the assumed utilities I've got, what I get is this nice expression. So I have x2 equal to eu star divided by x1 minus phi1 to the alpha 1, the whole thing to the 1 over alpha 2. Because it's not terrible, but it's not really a thing of beauty. However, if you work with this thing a little bit, we get a much nicer expression. And here it is for good x1. That's that the demand for good 1, and I've been using x sub 1 of py for Marshallian demands. You can use little h's to denote Hicksian demands, so h for Hicks. So the Hicksian demand is equal now to the number e raised to the level of utility u star divided by alpha 1, all times a ratio of prices, p2 over p1, times this ratio of coefficients, alpha 1 over alpha 2. This whole thing raised to the power alpha 2 divided by alpha 1 plus p1. Okay, so that actually is a reasonably beautiful expression as these things go. Okay, having solved this thing for x1, which involves some screwing around with algebra that I'm skipping, it's really nice to be able to compute x2 easily just by symmetry. And so you can use symmetry to solve for x2 just by basically going through this expression for x1, and everywhere you see a 1, make it a 2, and everywhere you see a 2, make it a 1, and by a symmetry argument, that's got to give you the Hicksian demand for the second good. So I have exactly the same thing here, except that everywhere, as I said, there was a 2 up here, there's a 1 down here, and vice versa. Okay. All right. Okay, so those are Hicksian demands. So the arguments of these things, as promised, are no longer prices and income. Instead, they're prices and level of utility u star. So these Hicksian demands are the answer to what question? I want to improve that a little bit. Somebody else try? Well, it's not income. So, yeah, hold on. Yes. So I like that's a little bit poetic, isn't it? But great, yes.
The amount of x1 I would consume were I to minimize the amount of income I would achieve utility of each
That is less poetic but precise. So it's the if I'm going to turn it around a little bit. If I choose the expenditure minimizing way to achieve a level of utility use star, the Higgsine demands tell me how much of each good I should purchase. So I should purchase this much of good 1, this much of good 2, and that's the cheapest way to achieve a level of utility use star. Okay. All right, very good. Okay. Let's see. I want an application here in a little bit. I'm going to tell you one more mathematical tool. We'll do some applications next time. So that's the expenditure function. So the expenditure function is analogous to the indirect utility function in the same way that the Higgsine demands are analogous to the Marshallian demands. So, and in particular, we're going to define a function, and I'm going to use the notation E for it. So the expenditure function depends on P and U star, and it is a quantity measured in dollars or whatever accounting unit we're using. It is the expenditure necessary to achieve U star if you go about achieving U star in a cost minimizing way. Okay, so and that's just what it says. E of PU is equal to the minimum expenditures necessary to achieve this level of utility U star. Okay, now to compute that is straightforward. Once you've got the Higgsine demands, and we do have the Higgsine demands, they're right here. What we do is just the same way, it's the same method we use to get the indirect utility function. We just take the Higgsine demands, plug them into the expenditure function. So where we have an expression for x1 here, we take this thing, plug it into the expenditures, take this thing, plug it in for x2 in the expenditures. So just this. We wind up with expenditures being equal to P1 times H1, where that H1 is the Higgsine demand for good 1, plus P2 times H2, where H2 is the Higgsine demand for good 2, and so on. There might be an easy way to do this. When I work this through, this actually results in a heinous mess of algebra. But if you don't make any mistakes, it all turns into something quite beautiful. And here it is. The expenditure function for these references we've been working with are just equal to a constant a, and that's again some funny function of the alpha, so we don't worry about it too much. So it's a constant a times the number e raised to the power u star, so that's fine, times each of the prices raised to their corresponding reference parameters. So times p1 raised to alpha 1, p2 times raised to alpha 2, and so on. You can see, by the way, very easily how to generalize this to n goods. You just keep on multiplying the prices raised to their little powers. And then you have to pay for the minimum level of expenditure, so the sum of prices times these subsistence parameters, and that's the expenditure function. Okay, now gazing at that expression, how do expenditures change if we increase prices? That almost sounds like a trick question, but it's not. If prices go up and you still need to achieve the same level of utility, your expenditures have got to go up. And you can see exactly how here. You have to pay more for the minimum bundle that involves these fees. You also have to pay more for the rest of the stuff you decide to buy as well. So if prices go up, expenditures go up. What if the level of utility? What if you decide, well, U star isn't good enough. I want U double star. So the utility you're trying to achieve goes up. What happens to expenditures? Yeah, so you got to spend more to get more utility as well, which is perfectly intuitive, I hope. Okay. All right, I'm going to stop there because I'm out of time, and I will see you Tuesday. Have a great weekend.